report, waste again. All right. Got your lattice back. If you got an A on a section, as I said in the email, you don't have to write that section. Probably the easiest way to do it, so it's not like crazy looking, is just to put your number, like say you got a 94 on the introduction. So format the paper like you normally would, the little title page, put or the abstract, just put abstract and put 94 where the abstract would go, or 94 where the intro would go, or wherever the method would go, or whatever, right? Just do it like that. Does that make sense? All right? If I gave you a prompt, right, for the discussion. If you got an A on the discussion, I gave you a prompt in that email. And that was the last one, so I said that. So if you got an A on the results section, I want you to report the F values. I want you to report the significant results. You don't have to describe what they mean. You don't have to do whatever. But I want you to put your figure and your stats in there. Show me you did the stats and the figure. Right? That's all you need for, you don't need text for your results. For the discussion, if you got an A, I still want you to answer that prompt. Okay? Like, how does masking, what did it mean about masking influencing? How's that related to this? Right? So just answer that in a few sentences. Good to go? Questions?
Kate, did you put that prompt where?
In the email with your grade?
Okay.
I'm pretty sure I did.
Just like the question?
Yeah, I had like a question. Answer this question in the discussion if you got an A on the discussion. Okay?
How much are you expecting from that?
If you got an A on the discussion,
Yes.
just show me you know what the answer to that question is.
Do you want me to paragraph?
If it takes that, if you can answer in one sentence and it's clear that you understand that, then I don't care. But make sure it's clear to me that you understand.
What exactly is the prompt? It wasn't in the email.
It wasn't.
Just
I'll send a. I was really rushing to get those back to you guys as fast as possible, so I will send an email. I'll make a note to send an email.
It's the last sentence. You still need, it's just not a question, you still need to explain how the masking tone created the results that it did.
Okay. How did the masking tone create the results it did? Answer that question. Last part of that. Cool. Okay. All right. So we are doing review for auditory and vestibular system today. Exam on Thursday. Next Tuesday, I'm going to do a lecture on development of sensory systems. And then Thursday, review for the exam, and then you have your final exam, and then we're done. I think our exam is on Wednesday? Tuesday? Okay. So if you, I know it's kind of early, but if you'd like to take it earlier, that's fine. I'm okay with that. If you have 2 exams on Tuesday and you want to rather take it on Monday, just email me, let me know. You can do that, okay? I want y'all to have the best exam week schedule possible. I know it's hard to take 2 exams in the same week. Okay? So I'll work with you on that. All right. Questions? Yes.
What is fundamental frequency?
Fundamental frequency, right? Fundamental frequency is the main frequency associated with the tone. So unless I'm presenting
It's out before that. That's it. I checked.
yeah, okay. So it's easier for me to show with this, right? So unless I'm presenting a computer tone, right, a generated tone, sine wave, that only has one frequency present, obviously that would be the fundamental frequency. But in nature, unless it's something computer generated like this, right? There's going to be a primary frequency and then other frequencies that are harmonics, right? So here, the pure tone for this note, which is C4, which is 262 hertz. That's 262 hertz by itself. Here are 3 instruments, piano, trombone, and tenor sax, that are all playing. It's hard for them to hear me on the recording. That are all playing that same note. So the fundamental frequency is 262 for all of those. Now, when it's not a pure tone, you see that there are a lot of other frequencies also present when that instrument plays that note. We hear the fundamental frequency as the tone, the tonal quality of the sound, right? But the richness or character of that fundamental, of that instrument, belongs to the secondary harmonic frequencies. And that's why, you know, a tenor saxophone sounds different than a piano. One reason, another being attack and decay. But, so I can demonstrate that here with this, right? This is the fundamental. So if that's a fundamental frequency, right? Here I've added in 3 additional harmonics. And so you're still going to hear this fundamental frequency, but it's going to have additional qualities. Right? It sounds, the quality of it's different, but the fundamental frequency is the same. Does that answer that? You good?
Yeah, so how does that relate to pitch? Because that's the point that we have, is understand that it related to pitch.
Yeah, so that is, it's the pitch that we are perceiving as the primary tone. So pitch and fundamental frequency are the same.
Okay, thank you.
Yes, Bakery.
In that same review point, it talks about how the notes are related to pitch.
Yeah.
Or just understanding notes. I don't understand what a note is in general. Or I know what it is, but I don't know how to like.
Right. So, see, I should have brought my little synthesizer in. Right. So, somebody in the world may understand this who specializes in research on music and pitch. I don't fully understand it. I don't think most people do. But if I go to a piano and I just start playing, if I play a note, and then I keep going up and say, tell me when I play that same note, you'll tell me when you hear the same note. And it'll be 8 notes away. And I don't know that we understand why humans perceive those intervals as belonging together. That's tone chroma, right? That's tone chroma. That an A and an A and an A all have the same tone chroma. And if you play this A and that B, there's a discord and it's not the same tone chroma and it doesn't sound the same to us. Even though these fundamental frequencies are getting higher and the pitches are higher and the tones are higher, they belong together perceptually for humans. And I don't know, someone probably understands that, but I don't know why that is, right? But it's universal for humans in any culture, right? That these notes are organized in this way, right? So, so we group those as a set of 8 tones. and they repeat.
And that's an octave.
And that's what?
An octave.
An octave, yes. Yes, that's an octave, is one set of those equals. And it could be from B to B, or it could be from A to A, or D to D. Those are all octaves, right? It's not like a set thing. It's just the group of 8 that all have different tone chromas before you get to another note that has a similar tone chroma to what's in that 8. Does that make sense? Okay, Karen.
So are there 8 fundamental or 7 fundamental frequencies that change with each, like, go up in pitch, or is every single note
Yes.
A through G in all the different?
They're going up in fundamental frequency. Or
So
pitch.
every note has a fundamental frequency.
Yes. It's lower or higher than the note before or after. Right? The note before it's lower, the note after it's higher.
So it's not like categorical everything.
That's probably more than you need to know about frequency and pitch. All right. Other questions? We got all your bottom-up stuff? Yes.
What's phase lock?
Phase lock. Okay, good question. So that is involved with neural coding in the auditory system. In the auditory system, there are both label line and cross-fiber pattern coding. Label line is pretty simple to understand. The cochlea is organized from low frequencies in the innermost part, all the way around to high frequencies at the outermost part. The place on which the cochlea is being stimulated corresponds to a frequency. Therefore, it's label line for that place, that frequency. Okay? Now, under 5,000 hertz,
It's the next power pattern.
maybe the easiest way to say this is above 5,000 hertz, the frequency is so fast, above 5,000 hertz, the frequency is so fast, and we have so few receptors to cover 15,000 hertz. And these sounds happen to be a lot less meaningful to us in terms of not being part of our language, right? That we only have place coding here, right? Which means if I stimulate here, in order to discriminate between that 7,000 tone, I have to move further away, right, in order to know that's a different place. And so, if I have to move down here before I can tell, I'm already 500 hertz below at 6,500, right? So that's that. Now, below 5,000, we also have place. So if I stimulate right here, right, that's a place, and it belongs to 3,500. But I have so many receptors packed in there for that if this is that tone, right, no one neuron can fire on every peak because of the refractory period, because it's too fast for the refractory period. But if I have a whole bunch of neurons and they're all randomly kind of firing at different peaks, and I look at the volley of action potentials coming from that area, that volley is going to approximate or represent every peak. And I'll be able to count that and say, hey, that's 3,500. And if I go to 3,505, which is not very far away from here, it would be hard just on place to know that I've only moved 5 hertz. But because I have the volley and can count 5 more peaks, I can discriminate that. And that's the across fiber pattern. because it's across this group of neurons all coding with the same frequency, that I can see the pattern representing the hertz. And that gives us better discrimination in the areas that we wanted. Good. Yes.
For the amplification in the middle here and the mechanism,
Mhm.
for the two mechanisms, is one of them pressurization of the membrane?
No. So, there are two mechanisms to amplify the signal in the middle here. One are those bones. Okay. One are the fact that these three bones move in a lever-like way, so that right, if I move this end of the lever up and down just that much, right, it's going to make this end go up and down that much, right? That's the way the levers work, right? A little movement here is going to cause a bigger movement over here. So that's one way in which, that's the way the bones work. So the bones do the lever-like action, right? The second one, I take a really big area I vibrate this really big area of the tympanic membrane, and then I concentrate it on a much smaller one. That also amplifies it, because a little movement here is going to cause a bigger movement there, right? We're catching a small movement with a big area, and funneling it down, right? So we have a funnel action based on the size of the membranes, and we have a lever action based on the size of the membranes. Does that answer that?
So what is the round window?
Yes. So the oval window is where it comes in, right? And it bounces all around the cochlea. And then it gets to the end of the cochlea, and if I don't release it through another membrane, it's just going to hit this wall and bounce back through and keep bouncing back around in the cochlea. We only want it to go through the cochlea once. Otherwise, we'll hear two sounds, right? So when it gets here, the round window expands and dissipates the wave so that it can't reflect and go back. Good questions. Yes, no.
So wait, does the oval window like dampen amount of signal coming in, or is it just like almost redirects but not too much?
No, the oval window is this, it's replicating, right? It's creating the wave. These bones are pushing against it, making a fluid wave that matches the air wave here. Yes.
Can you explain the anatomy of being able to determine inaural time differences?
Yes. So what does inaural time differences?
The time difference between the sounds hitting the ear.
Yes. Right? So we have three waves, right? then we can localize sounds. Because our brain, our whole auditory system is not set up to identify where sounds are coming from, but rather to identify what frequencies those sounds are. It's tonotopically oriented to identify the frequencies that are present, right? So we have to have specialized systems to do the auditory localization, okay? I'll talk about inaural time differences last. I'll talk about the other two first. So the first, we have two specialized ones. One's for low frequency sounds, one's for high frequency sounds. Low frequency sounds are going to come in, and if the frequency is low enough, it's going to hit one ear in a different phase of that cycle than it hits the other ear. And that's going to cause the eardrums to be pushed in or pulled out in a different way. Because remember that cycle wave are compressions of air and expansions of air. And so we have a mechanism that can tell if our eardrums are out of cycle, out of phase, and can help determine what that phase was. Only good for very low frequency sounds. As soon as the sound wave can go through a whole phase, then we lose that ability because we can't compare one to the other because we don't know how many times it went through the phase before it got to the other side. Okay? Only for low frequency. For high frequency sounds, they get absorbed by stuff, by matter. Matter absorbs high frequency sounds. Matter doesn't absorb low frequency sounds very well. So this doesn't work for low frequency. For high frequency, one sound is going to hit the first ear louder and be slightly softer because it got absorbed in the second ear. And that's an intensity difference. But it's only good for high frequency sounds. Because low frequency sounds don't change their intensity because they don't get absorbed. Any questions about that? Phase? All right. We also have a whole nucleus in our brainstem dedicated to detecting the time difference when sounds hit our ears. So if it sounds directly in front of me and hits my ears at the same time simultaneously, right, I can tell that it's simultaneous. However, if there's a sound 10 degrees over here, it's going to hit my left ear, and then there's going to be a slight millisecond delay before it hits my next ear. So let's draw 5 neurons. And this all happens in what nucleus? Yes, the SON, right? So if we have, these are all going to be now labeled line outputs for where in space that sound came from, based on the timing. So the center one's going to be 0 degrees, right? Okay. That means that if a sound hits my ear here at the same time, the sound hits my ear here, right? They're going to travel at the same speed. Can't do this because I have a microphone closed. They're going to travel at the same speed, and when this one gets here, this one's going to be here. Do they match up? Do they coincide? No. And then this one gets a little bit further and activates this one, and this one activates that one. Do they coincide? Meaning, are they activating the same neuron? No. And then they go a little bit further, and this one activates this one, and this one activates this one. Now do they coincide? So now, then, we get a firing signal goes down. It goes, yeah, those hit my ear at exactly the same time, and they met up on this neuron because they started at the same time. Right? Actually. All right. I'm not making too messy. But So we're going to say this is our right ear, right? This is our left ear. Now, a sound is 5 degrees, or let's say 10 degrees to my left. Which ear is it going to hit first? My left ear. So we are starting here, and we are moving. We are already moving, and now we're waiting, and now the sound hits my right ear second. Moving along, this guy's moving along. And they hit this at the same time. And so now I get a signal coming out that says, "10 degrees left." Good? They coincide. So when this happens, the signal that hits the ear first goes for right? Because it gets a head start. It's already at 0, and this one hadn't even started, right? And so they meet up on the other side, where this one had to travel longer because this one was delayed because it was the second ear. If we went the other direction, now let's say now we're 5 degrees, let's say we're 5 degrees to the right. It hits my right ear first, starts traveling along, right? Hits my left ear second. Delay. And so they're going to match up. Here, and we get right? So you could label all of those, I'm just making this stuff up, right? But this would be 5 degrees left. The other one would be 10 degrees right. So these end up being and I'll take a picture of this and post it for a minute. But this is how the SON works. And the reason I want you to know this is, it's really, if you think about what it's doing, it's a pretty simple architecture, a circuit board that's set up on timing. The only thing that has to happen is they have to meet at the same neuron. And they'll always meet at the same neuron because of the time at which each ear got stimulated. And because of this, it allows us to do remarkable sound localization, very good sound localization, very precise, within milliseconds difference for any frequency sound. Doesn't matter if it's high or low. So this works for everything. Phase only works for low frequency. Intensity only works for high frequency. Other questions?
Can I go over transduction again?
So, there's like a multi-step process leading up to transduction. The transduction itself is like a three-step process. The textual membrane bounces against the cilia and opens potassium channels. And potassium comes in. That's the first thing. All right? Potassium opens a voltage-gated calcium channel. Calcium comes in. Second thing. Influx of calcium releases neurotransmitters. It's the third thing. And then it uses energy because pumps have to pump all the stuff that came in that way. That's transduction, that little part. Now leading up to it, you have the pinna catches and collects and funnels the sound into the middle ear. The middle ear amplifies the sound to the inner ear. And then the shape of the cochlea determines where the tectual membrane will bounce, the place at which it will bounce to cause transduction to happen. But that's not transduction. That's just getting the sound wave to the point that it can be transduced. Transduction is textual membrane opens calcium channels, calcium comes in, potassium comes in, sorry. Opens potassium channels, potassium comes in, potassium opens voltage-gated calcium channels, calcium comes in, calcium causes neurotransmitter. Yes?
Can you explain the Doppler shift one more time?
The Doppler shift.
Yes.
All right, so this is what we just drew on the other side of the board. All right. Okay. So when you have a sound like an engine and it's moving slow, all right, the sound vibrations coming off of it are about the same distance apart in the front of the car as they are in the back of the car. So you would perceive this frequency the same as this frequency because the sound waves are the same distance apart. However, if that car or plane or whatever is moving fast, as it produces the waves, because it's moving in that direction, they're actually closer together. Because over here we have the time that it moved, right, making these further apart behind it. Which is why when an engine goes past you at a high rate of speed, before it gets to you, it sounds like a high-pitched sound, higher-pitched sound, and as it's now past you, the sound that remains is a lower pitch sound. So it starts as a high-pitched sound and transitions to a lower pitched sound. If you're in a jet that can go faster than the speed of sound, it's actually here, and as it's generating that sound, the sound can't even get in front of it. So there's a big wall of sound right here, and then it trails off. And that wall of sound is a sonic boom that we hear. apparently, I don't know if y'all are aware of, but now that we have like transitioned our space program from, it used to be that NASA would fly all the satellites up into the sky and we would just, the boosters and stuff would be space junk or they'd fall back in the ocean or something like that. And now that we're paying SpaceX and these other private companies to fly our satellites up there, they're returning to Earth and reusing the boosters over and over again. And so every time the booster comes back in, it creates a sonic boom. And so like all up and down the East Coast this year, people have been complaining about hearing these sonic booms as they recover these things because it sounds like a bomb goes off. It's like an explosion in your house. Other questions? Those are great questions.
For speech production, do we just need to know like literal biological mechanics of it? Do we need to know what?
For speech production, I'd like you to know what is a phoneme. You do not need to memorize all the phonemes. I'm not going to ask you what the phoneme is. Okay? But you should know what a phoneme is. You should also know the fundamental difference between consonants and vowels is that consonants use restricted airflow and closing and opening are articulators. Lips, teeth, tongue, jaw. And vowels primarily use frequencies with open mouth shapes as opposed to constricted. So that's what I'd like you to kind of know about concept. And to appreciate the ability of changing one phoneme to change the meaning of an entire word. Those phonemes are actually very important, and our ability to detect them determines our ability to correctly identify what words we're saying. That's fine.
When you say speech perception is resistant to degradation, is that meaning, what does that mean?
So the degradation means that there are all sorts of things in our environment interfering with sound waves, like over masking them, right, because they're louder, or distorting them. And so that would potentially impact our ability to hear speech if you can't hear every single frequency, right? But because if we're able to see people's lips moving, we learn that certain mouth movements mean that certain phonemes were made. Therefore, we trust our eyes. If I see your mouth make a duh and not a thuh, then I use the signal from vision that I know isn't interfered with, isn't degraded, and trust that and perceive that that's what happened. Even though from the auditory system, the McGurk effect, right, we actually heard the, but we perceived it as fa because the lips didn't fa. And that helps us because all the time we're having a hard time, it's hard to hear every single frequency that's coming in, right? And it's why we use context, not just vision, but context, why you could, read that language with all the missing letters in it and still make sense of it because you knew that based on that pattern of frequency, the missing frequencies had to be this to make this work, or context of the sentence. I saw a clip on CNN yesterday at the gym, on the treadmill, and they were covering a high school of all deaf students, and their football team had made it to the state championship in California. And they were talking about how some people felt like they were at a disadvantage, but they were using sign language for all their plays and to communicate on the field, and nobody could take, could intercept their plays because they didn't know sign language. And one of the players, the deaf player, said, and because vision can't be interfered with, it's not like I can't hear what you're saying, coach, over the crowd. I can see exactly what you're saying. They said that was an advantage because their vision wasn't degraded like normal football players' hearing is. Which is why on the football field they use those big funny signs to call plays in, because that doesn't get interfered with, like trying to call a number or something. Lots of practical uses for this stuff. Other questions? I'm happy to stay in here and answer questions. I mean, if you literally don't have any other questions, we don't have to torture ourselves to sit here. So you're free to go. And if you have a question between now and Thursday, you can shoot me an email. My eyesight class this morning, I told them they could hit me up on email, and they all laughed. Maybe I should go shoot them. I don't know. Yes.
What's the neural coding
For what? For vestibular. So the neural coding for vestibular is for the otolith organs, it's labeled line. For the horizontal orientation, meaning upright to gravity, or forward or backward, meaning face forward or lay on my back with the other otolith, horizontal, right? So that's all labeled line for that one. For the semicircular canals, but each semicircular canal is orientated in a direction. So that's labeled line for moving in that directional area. 3 different directions. But then if it bends in one direction and excites the system, that would be, say, acceleration. And if it inhibits the system, then that would be deceleration. So the across fiber pattern, whether or not in that directional labeled line is excitatory or inhibitory, relates to acceleration or deceleration. I'll also take this time to tell you that we have a new course evaluation system. It's all electronic. You probably should have got a link to it. And every professor is being evaluated every semester in every course now, where it used to rotate around. I really appreciate that. I've always wanted to be evaluated more because I like your feedback. I like to know what has worked, what hasn't worked, what you learned, what you're supposed to learn. So I do want good response rates, and if you can take some time between now and the end of class or when the exams are over to do that, I look at that stuff and try and interpret it. So. All right. Any other email? It's always going to be like 5 years behind the sliding. It's going to get complicated. This I know it's
I'll give you guys
Someone wants to
issue text.
I don't want to see how they're going to come back.
Okay, perfect. Thank you so much.
Actually, I have a question about the lab report. Is this relevant information to put down, how many actual like auditory signals or like the PowerPoint count them or specifically for like the
Oh, you mean for like on each slide?
because, well, yes, there's a like on each slide overall.
Yeah, well, I mean, I think you need to state what frequencies were represented, right? And then there were two trials for each.
I have that.
I mean, they're not two trials for each decimal. I mean, no, you don't need to get a good count for a total number. I mean, that was what, 168?
I know it's a lot, I just didn't know if
Yeah.
that was wrong.
No, just the 2 per decibel level and the frequency.
Oh, 2 per decimal. Got it. Thank you, sir.
Yeah, they want us to get like a conversation.
Yeah.
No, I said that.
Thank you.
Is that right now? Sure.
Have a good day. At the airport. Dr. Goodman,
Yes.
so if I'm just writing the results section, it's just the results and discussion. Do you want it like APA formatted and like, do you want me to go through every section and play time or whatever? Okay. Okay. Have a good rest of your day.
Yes, I'll see you at 4.
Thank you,